Okay, in this problem we were asked to find in the statically indeterminate situation what the reactions were, and we went through that in the previous email, all the 5 steps that we took first to get to the reaction value, the redundant reaction value, and then we went through equilibrium then to find the other reactions on the system. But we've also been asked to find the shear moment diagrams, equation for the elastic deflected shape, the equation for the rotation at B out here, and to draw the qualitative to consistent deflected shape for the beam. Right, and that's what we're going to go through next. Right, so let's start with the shear and the moment diagrams. There's a couple of ways that we could have decided to approach this, and first we could just start from the free body diagram that we have from the final answer, and that was, here's the equilibrium or the free body diagram of the final. We had found that By was this 3/2 m naught over L when we imposed m naught. Then of course there's sum of forces in Y gave us the reaction at the other end, and then the sum of the moments gave us this reaction at the left. Both of those moments are going in the same direction and equilibrated by a force couple going in the opposite direction of those two, and from which then we can draw the shear diagram following downwards here, the direction of the concentrated force coming over. There's no distributed load, so constant here, then closing off, going back up. Right, so there's your shear diagram at the final, that what we call the composite of all that. And then draw the moment diagram. We got to start off with a smiley face at the left hand side at m naught over 2. The slope of the moment diagram given us to us by the shear, which is negative throughout, and it's the same value of shear, so it's a straight line all the way through. And when the change in the moment, it's this area, so 3/2 m naught over L times L is just going to be a negative 3/2 m naught. Add that down, we get to the minus m naught, and that matches with the frowny face moment we have over here on the free body diagram. So that would be one way that we could do it. Now the other way to do that is we could have followed the same approach that we used to come up with this reaction to begin with, and that's by parts, right? A cantilever beam with the imposed moment would be pure bending here, so there'd be no shear, and we'd end up with just negative moment throughout. That would be uniform. That would be the moment diagram associated with just the cantilever and the applied load. Right? Then we come back and we impose the By value. Right? Now that's going to have a non-zero shear throughout. That's where we get this. And then the moment diagram that goes with that is going to look like this triangle with the max at the left end. Right? This times the moment arm going increasing over here to the left, and so this increases linearly up to that 3/2 m naught. Right? And so we could think about this composite as being the sum then of these little individual parts. And notice when we look at that, this is pretty easy for the shear. The final is just this 0 plus this one here, so all the shear happened to come from just this case. Right? But over here, notice that we get this little mix of positive and negative moment, and that's coming from first this pure negative moment that we have over here plus this triangular variation. Right? Now there's a couple ways that we can look at this. One of which is, note, in a sense we start with that rectangular one, this one right here, and then we superimpose this one here, sliding it over where this becomes the new base of the triangle, bam, and so then our net moment is that right there. That's one way to look at it. You could also look at it as taking this and putting it right up here. Would be another way that you could kind of look at it, and then we sum those two to get to this composite. It's another way to kind of play with it, that the values say right here is the sum of that value and that value. The sum at this location would be sum of that value and that one, so on and so forth. There's two different terms in the expression, so to speak, to get to this net composite. Right? Now that we have the composite moment diagram, and note the 2-to-1 ratio, which means the inflection point happens at the 1/3, 2/3 point. Right? M equals 0 is going to be our inflection point. Right? Well, then you take this and go back to our deflected shape that we had posed a long time ago. Right? And that is, we've got positive moment here, so concave up curvature in that region, negative moment in the latter 2/3, so we have concave down and the curvature there, and that's approximately what I've got drawn here. Probably could have put this transition point, maybe, I don't know, that's pretty close to about the 1/3 point. We have 0 rotation at A, because that's the fixed end. We better not have any rotation there. It doesn't go up and down, so we're good there. It doesn't go up and down at B, so we're good there. We're going to end up with negative slope over here. That's something to keep track of here in a little bit. But that's generally how we could get this consistent, qualitative consistent deflected shape that we've been asked to do up in the problem statement, is we have to draw the final moment diagram first before we can draw this shape in. Right? And then a couple more pieces we've been asked for. We want the rotation at B, so we can use superposition again. We got the rotation at B from the cantilever with the m0 applied. That's this first expression. We've got the rotation when we put the redundant reaction back in. Here we go here. Now we know what By is because we've already determined it. Substitute that in right there. And then the rest of this is just solving, reducing this, simplifying it down. And note theta b equals a negative value when m0 is positive in the direction shown, which just says that we ought to have a downward slope right here, and that's exactly what we've got drawn, and that's what we've ended up developing for that expression. Right? Alright, so then the last thing that's been asked to find is the equation for V, the deflected shape. Right, now let me get rid of some things here. There we go. Alright, so now again we're going to use superposition. Right, we're going to take part 1 plus part 2. Part 1 and part 2 are from right here and here. Right, so all we have to do is go look up the expression for the deflected shape for m0, or derive it. M0 being applied on the cantilever beam, and then same thing for cantilever beam with the By, and that's what we've got written down here. Right? You need to go and look that up in the table, verify that these are the equations you would have pulled out as well, and then I have substituted in for P, which is really By in that instance, which is this little part right there. Right, and I've done a little shift over here, put the 2 and pull the x squared out. That's still multiplied there. I'm doing that thinking ahead about how I'm going to organize this, because then I factor out an m0 over ei and get this lovely expression here, which can still be simplified here. We're going to have some x squared terms. The L over L is going to cancel out in the first part of that term, and when you do that, then note this simplifies down into something a little bit nicer ultimately, and then the 4 can come out, and then I do this other goofy thing of even factoring out an L squared so that I get an x over L along here. And when you do that, what you end up with is a non-dimensional version of this, and that is we got this m0 L squared over 4ei factored out. We can now look at this zeta equals x over L. Zeta is just how far along are we in the beam. Are we at the beginning point here? That would be zeta is 0. The end point, that would be x equal to L, or zeta equal to 1. And now zeta is just a fraction of, well, where are we at along the length of the beam? It's a very convenient way to set this up. Right? And this is called a shape function. So let's check a couple of properties. When zeta equals 0, that means we're at the left end. Then 0 minus 0, and the deflection would be 0. That's what's supposed to happen. When we're at the right end, x equal to L, zeta will be equal to 1. And we'll have 1 minus 1. So once again, the deflection will be 0. So that's exactly what it should be. In between, then, that means that zeta will always be either greater than 0 or less than 1. That means zeta squared is going to be greater than zeta cubed, and that means this little portion here will always be greater than 0. It will be positive, and that means the deflection is always positive, and that's of course what we see in this proposed deflected shape that was consistent with the boundary conditions as well as the moment curvature that we ended up with. Right? Now, one of the reasons why we call this a shape function is that in real computer modeling, what we end up doing is looking at 3 different scenarios from which then we add all those together to get to the real situation. It's a superposition principle. Right? And what you're seeing on your textbook is actually, or on the pages, is that of a textbook that talks about the slope deflection method, but the finite element method, which is the way that most computer models now are developed, they're going to do the same thing. And here's the case that we just looked at. Here's a fixed end over here, and a moment has been applied at this right-hand side. You don't see it because that's a part of the derivation you don't see quite here on this page. And there's no up and down movement. That's the prop cantilever. These two are just mirror images of each other. Okay? Just mirror images and then another flipping going on here. Right? So almost the same kind of thing. This is the shape function we just derived. We can do something similar from here for this one. It'll look very much like that one. Right? So that takes care of a beam that would have rotation at its 2 ends. It could also have a chord rotation where one end slides relative down to the other one. That's another shape function. Those are the 3 that I was referring to. Right? None of these have loads within the member, so that's what this last case is actually all about, is the different ways that we might have loads in between. Right? So each one of these are called shape functions, and then there's one more little piece. You get into that into the both the structural analysis course a little bit, and then advanced structural analysis, being the finite element stuff, would put all that together. And that's what's really happening inside the computer model, is we actually superpose the results of these special shape functions together to get to a prediction of what's going to happen in the specific situation. That's a really difficult thing to work through by hand, and that's why by hand we would do things a little bit differently than what you see here. But that's coming up in the future of other classes and what's really going on in the computer.